Hey, dude. Have you read this thing called quantum computing? No. What is it? It's like a. It's like a. It's like a. It's like a. It's like a super fast computer. Okay. It's supposed to be super fast, and it's quantum. I think it's supposed to be super small. I got something super small. What? So a quantum computer is not like your normal computer. Forget about that. Because if you look inside a computer, you're going to find something called the CPU. Inside the CPU, there are millions of little transistors. These transistors are made of a material called semiconductors, which are basically just a substance that can just allow electric flow and stop it without any moving mechanical parts. This property basically is the basis of how all your CPUs work. Your current flows, it's on. If it doesn't, it's off, or ones or zeros. These are bits in which they can be 1 or 0, which you might know as binary, which is the language of the CPUs. And the total processing power in these CPUs increased by making the transistors smaller, making the distance between them smaller, or just having more transistors. So now we know how to improve our technology. What's the issue? Can we just do this for the next decade? Well, no, because science is weird. And when things are really, really small, they become really, really weird. Come on, man. The main problem with making these transistors and the distance between them smaller and smaller is that eventually you'll get so small that the electrons in the transistors could tunnel, meaning they can just pass through the insulating layers in the transistors, which basically means you can't do anything to stop them from flowing. And the problem with this is it's going to turn your zeros into ones and your ones to zeros. This will obviously cause errors. Now we've reached the limit of our computing power, and civilizations will stop, we will never progress, and a story done, dusted, go home, hug your family, we're all going to plateau. Remember when I said that the bits can either be 2 states, 1 or 0? Well, a quantum computer is just built different. The basis of your classical computers are bits, but the basis of your quantum computers are qubits. Qubits, like bits, can also have the 2 states, your 1 or 0. 1 is when the qubit is in a high energy state, and 0 is when it is a low energy state. But the thing that makes them special is they can also be in what we call a superposition state. In other words, both 0 and a 1. Take your typical coin. Let's say you flip it. If I ask you right now what is the probability of landing on heads or tails, you'd probably say 50%. Oh, what the fuck? But if you think of it like a qubit, it is now in its superposition state, both 0 and 1. This is superposition. This property allows for calculations that classical computers can only dream of doing. A common example is you take a maze and a rat, and the rat has to find the cheese. A classical computer would calculate every single possible route the rat could go one by one. But with a quantum computer, it can do all the paths simultaneously. Obviously, this is a lot faster. But here's the thing. We can't measure this superposition. The thing is, when a qubit is in a both 0 or 1 state, but then we look at it, it will either only be 0 or 1, not its original superposition state. And the information on what its superposition was is lost, just because we're looking at it. Obviously, this is a bit weird, because why the frick does a particle know I'm looking at it? Is it stalking me? Am I stalking it? Am I the weirdo? And it kind of makes you think the particle is just being super difficult and annoying. Guilty!
Hello there.
In any case, the reason why we can't observe particles in a superposition state is because the very presence of light affects the state of it. A thought experiment to explain superposition is Schrodinger's cat, which is a thought experiment to explain this unknown 0 and 1 state, and why we can't ever see it. Let's say we place a cat in a box, and right next to it we place a ticking time bomb of poison set to a random time. Nobody knows this time except the cat. And when you close that box, the cat is considered to be both dead and alive. And we don't know whether it is dead or alive until we open the box. So if we can't observe the state of a qubit, how are we supposed to use the superposition property to do these calculations? These things. Each superposition state has different probabilities. Let's take one qubit, which we represent with this sphere. The direction and size of the arrow represents how the qubit is orientated. Direction up is 0, direction down is 1. If the arrow is not one of these 2 states, it is in a superposition. How we separate the states of these superpositions is with probability. Let's say this arrow is lying dead right center between 0 and 1. This would mean that 50% of the time we get 1, and 50% of the time we get 0, and then so forth. Thus, different orientations will give us different probabilities of being 0 or 1. And by the way, the 0 and 1 symbols are ket 0 and ket 1, which are just labels for the ground states, i.e. 0 and 1. Another fundamental difference between classical bits and qubits are how many pieces of information you need to determine its state. Let's start with 2 bits. 2 bits have 4 possibilities. Therefore, I only need 2 numbers that are 0 or 1 to tell me if it's in one of these states. But with 2 qubits, you're going to need 4 numbers to tell me which state it's in. The thing is, qubits can also be one of these 4 states, but because it has this superposition property, you're going to need way more numbers to tell me whether it's in this state, or this state, or this state. Qubits have a probability of being 0 or 1, likewise for the other one. And then combining them will give you more possibilities and therefore more probabilities. This equation example how you describe a 2-qubit system state, where this triangle notation here is a vector, remember a circle? Yeah, this triangle basically just represents your distance and direction this arrow is in. Alpha's brothers and sisters here are just a bunch of complex numbers. Remember a sphere, when it's not on the x and y plane and extends the z plane, this is a complex number. Now this equation describes the probability of being any of these 4 states, which is why you require 4 numbers. As you can imagine, the more qubits you have, the way more information you're going to need. The formula for this is 2 to the power of number of qubits you have is equivalent to the number of classical bits. These probabilities are also another reason why quantum computers are not going to replace normal computers, as you have to calculate all the probabilities beforehand, and quantum computers will actually be slower for some things than your normal computer. So it's not like everyone is just going to have a quantum computer on their desk. You play Genshin? No, it's Wuthering Waves. Oh. Now, of course, if you have a bunch of qubits, you're going to need a bunch of numbers, and representing your data like this and working with this is really difficult. Instead, we now have to understand another property of qubits, entanglement. Let's look at this couple of particles. They're so cute together. Let's say they interact, have a wonderful love story, and then BAM! They separate. These particles are what we call an entangled state, where me affecting one particle directly affects the other, no matter how far they are apart from each other.
You can't stop our love!
This is really weird, and Einstein referred to this as spooky action at a distance, probably because it's pretty spooky of how no matter how far quantum entangled particles are, they will still affect each other. Couple goals. The more nerdy explanation of why it is spooky, though, is that when you affect one particle and then immediately affects the other, that signal has to be faster than the speed of light. But how does this property relate to qubits? Well, when you have 2 qubits together, their probabilities of being certain states really aren't independent. Let's say you have these 2 qubits together and they are entangled. Affecting the orientation of one qubit will affect the entire system. Okay, but there's no way you can represent this info with just these weird symbols, right? You're exactly right. See our sphere here? This isn't what a qubit looks like. We can rather look at what qubits are as they produce a wave function. And our actual state of our entire system of qubits are just each of the wave functions from each qubit into one. I haven't been completely honest with you. What? Quantum computing doesn't work. Well, now hold on there, partner. Quantum computing works. The thing is, these prototypes aren't 100% functional for many reasons. You see this whole alien-looking thing? That's your quantum computer. Cool looking, right? Firstly, remember our entire wave function? Well, because there's so many probabilities of qubits being in a certain state, some of them are actually wrong. Let's say my qubits produce either the answers 0, 0, 0, 1, 1, 0, and 1, 1. Thus, I have a bunch of wave functions. Now, how do I make sure I get the correct answer? This is where something called interference comes in. Interference can either be destructive or constructive. Destructive interference cancels out the waves, and constructive interference adds the waves together. And thus, I use destructive interference to decrease the probability of me getting the incorrect answer, and use constructive interference to increase the probability of me getting the correct answer. Now, here's the thing. This error rate is a bigger issue than it needs to be. Do you know why a quantum computer is shaped this way? Well, there's many reasons, mostly because it prevents external factors from affecting qubits, like temperature. Even the slightest of changes in temperature could cause the qubits to go haywire. And this causes the actual information you need to, And when these qubits in any quantum system is not affected by external factors, we refer to it as having coherence. Okay, bro, but what does quantum computing do? Can it calculate why my parents still love me? No, stupid. There's a lot of applications for quantum computing. The most notable ones are probably encryption, simulating quantum systems, which means we can test drugs, a bunch of other stuff, material sciences, optimization problems, a whole bunch of things. The one that I find interesting, though, is machine learning and artificial intelligence. Your most well-known AI right now is probably ChatGPT 4.0. And don't get me wrong, great AI, but it's no Jarvis. And there's a chance when quantum computing really hits the next level, AI is going to reach the next level. And who knows, maybe then it could tell you why your parents still love you.
Wishful thinking, petty goals, class grips and bruises.